So, in Phong Shading model, it actually has pretty much the same formula. However, instead of using colors like in Gauss shading, it uses normal vectors for finding out the color of each pixel or point inside a polygon. In the Gauss shading model, where we saw that for finding the color of each point inside a polygon, we used the C average and the proportionate values using their coordinates. In Phong shading, we literally find the normal vector of every pixel or point inside a polygon. That can be along the edges and also along all the scanning lines here. And how is this better? This is better because in Phong shading, it finds out the normal vector of each pixel inside a polygon. Then, using the normal vector of each pixel and the viewing position and using the Phong reflection model, which we have studied in the lighting chapter, it finds out the color or the illumination factor of every pixel, and then it assigns the color of every point. In this way, we can capture all of the spotting lights or highlighting lights even though they cannot be detected in the flat shading and the Gauss shading models. If you look at the example here, we can see that in these examples that we see here, right in the middle of this figure, we have a spotlight. Now, if we were using the Gauss shading would have basically started from these edges, these four vertices here, and using the average or the proportionate value using the coordinates of these vertices, it would have assigned colors to these edges and to the points which are here. However, it could not have been able to detect this spotlight color in the middle. But in using the Phong shading, where it uses the normal vector and ultimately the Phong reflection model, which gives us the illumination constant for every pixel and then assigns the color, Phong shading is able to provide this realism or this spotlight or highlighted areas inside our objects or graphics here. But it's not necessary or it's not true that Gauss shading almost all the time fails to show any spotlight in the polygons. For example, in this example right here, we can see that in this example, the spotlight area is actually on one of the edges of this polygon. So in this scenario, even though Phong will definitely be able to detect this, Gauss shading will be highlighting this point as well because this color is on the edge, and using the edge values or the vertex color values, we assign the colors internally in Gauss shading. So in this example, this will be able to detect the spotlight area as well, but most of the times it fails when your spotlight or highlighting areas are inside your polygon. But our Phong shading model brilliantly can detect that and give us a more realistic graphic. So now, if we go back and take a look at our examples here, since it's a bit messy, I might have to clean it a bit in order for us to compare. So now, if we take a look at 3 of the shading models which we have studied so far, in the flat ones, we see that due to assigning one specific colors to the polygons, we have a more rough looking textured graphics in flat shading model, but in Gauss it's much smoother compared to the flat model. However, we do not see any shiny surfaces or any spotlight areas in Gauss shading. But in Phong shading model, ultimately we see a much smoother surface here, and we see an absolutely spotted or highlighted area which is more realistic to us in the Phong shading models here. So comparing to these 3 here, we can obviously say that Phong gives us the best result, even though Gauss can be more quickly rendered.